Okay, now we are in the third lesson, or like, I don't know, sub-lecture, or how do I say it? Well, the fact is that this is the third video in my magnetic circuit course. So I'm not a professor or anything, I'm just doing this for fun. So it's midnight, I'm kind of tired, so if I say something wrong, don't, be mad at me. Well, now we are going to study the magnetization curve. So, in my previous video, lesson, magnetic circuit 2, magnetic equivalent circuit, you can watch it if you didn't watch it. You saw some formulas, BH, you saw in the first video the BH relation, and so on and so on. But the fact is that you're never going to calculate the magnetic flux by the magnetic flux density and the magnetic field with formulas, but with these curvatures, as you see here on the left. So every magnetic material has its own I don't know how to say it. It acts differently. One material acts differently. One can have more magnetic fields than the other. Ideally, it would be nice if we could pump the magnetic field intensity to infinity, so that the magnetic flux density gets higher and higher. But in real life it's not like that. It's something like this. So when you have a small amount of the magnetic field density in the magnetic circuit, then you will see that magnetic flux density is growing linearly. But this is the low reluctance area. There is a point where we can't make this go higher. We can theoretically go with the magnetic field intensity to infinity, but it has its own saturation point, and from this point to the right, the curvature, the line is steady. So you have almost the same amount of magnetic flux density in the magnetic material. So here is another figure where I show you some of the most commonly used magnetic materials in electric machinery. That's cast iron, cast steel, and silicon sheet metal. So, what makes this magnetic circuit act magnetically, or as a magnet, or a magnet carrying energy? Well, I can't remember, but it was like when I studied that in my first year, we had a magnetic material, I don't know, and we had little ions, and every ion, or an electron, I can't remember, but I think it's an ion, has its own magnetic dipole. So it's like this, and they're randomly positioned. There are random directions with interaction between these ions. But if you put a magnetic field intensity across them in this direction, and if you increase it more and more, then all these ions, dipole torque or whatever, go in a steady line. So they all want to show in this direction. So as more you pump this magnetic field intensity into this magnetic material, the bigger the magnetic flux density is going to be. But there is a point, and that's the saturation, where you can't make these ions look at their magnetic. You can't make these ions more uniformly. You can't make them look at the same direction. Those dipoles. You can't make them. You can make all of them in one situation. When you pump this H really high, then all of these ions look at their magnetic dipoles look at the same direction. So as long as you pump this, when you already all the ions look at the all the momentum dipoles of these ions look toward one direction, you can't make them look more into that direction than it is already. So there is a point H that you can go to, but more you can pump it as long as you want. This B will stay the same, so it is saturated. That's like when you have students in this room and you have, I don't know, 100 students, and you say, everybody please look at this white table, oh my god, this whiteboard, and maybe 50 of them are going to look, 50 other are going to watch somewhere else. Then you start to yell at those 50, come and look at it, and maybe 40 more looks at it, so you have 90 out of 100 students that are looking at that whiteboard. You go to those 10 who are not looking, and I don't know, you start to slap them, you start to kick them, you start to yell at them, and in one point you have 100 students looking at this whiteboard, and you put much more energy to make them look at that whiteboard than in the first place when you had 50 students, make 50 students look at this whiteboard. And everybody now is looking at this whiteboard, and you want to more yell at them, and you can yell at them as loud as you want, and louder. Everybody is already looking at the whiteboard. So pretty much the same analogy. You can pump the magnetic field intensity as long as you want. The magnetic flux density is going to stay the same. It can't go higher. And here are some magnetization curves for three various materials. So that's our cast iron, cast steel, and silicon sheet metal. As you can see, the silicon sheet metal is the best magnetic material. I don't know if I can say we have today, but pretty much it's the best. So this is always a better choice, but it's more expensive. So you always have to, if you're designing machine or anything like that, you always have to look at the cost of that and the application of those machines, you know, for what are you using them. So these are three various types, and you see in various values they, you know, change like this. So this is experimentally measured. So you know, you always have these tables somewhere, so you don't have to, you know, be careful with the formulas. And for example, if you want cast steel to be 0.7 Teslas, you just find the amount of magnetic flux intensity that is needed to give to that magnetic material, so you will get 0.7 Teslas in that magnetic material. Now, the air is kind of, only material or medium that can go to theoretically go to the infinity of B, the infinity of the magnetic flux density is air. The air can go to infinity and it's linear pretty much, but the relative permeability of air is 1, so you have to put a lot of current that can go in, you don't know where, to make the satisfying magnetic flux density. So air is a big problem in electric machinery. And now we get to the basic design of electrical machines. That is not a transformer. So this is kind of a rotational machine. It has a stator and a rotor. Don't worry, we're not gonna learn about that stuff right now. There's gonna be another course about it. But as you can see, between the stator and the rotor, there is an air gap, and that is a very big problem. Maybe the biggest problem, I think, in electric machinery. So these air gaps are usually very small. You will see in the example we have in my next video, we're gonna calculate some things, that we have to make these air gaps very small, so the reluctance of the air gap is smaller. Okay, now so there are in motors, machines, a lot of this there is air gap, except the transformer. Transformer doesn't have any air gap, and they don't have any mechanical parts. So the transformers have the biggest power efficiency of all the electrical machines. Okay, so here are the formulas for the reluctance of the core. C in index is core, and G here is gap, air gap. Now we have a basic magnetic material, magnetic circuit. As you can see, we brought the MMF, magnetomotive force, here, which is equal to HC LC plus HG LG, magnetic field intensity in the core multiplied by the length of the core. This length of the core is the middle line of the magnetic material, so it's always the middle that you measure, plus the magnetic intensity field in the air gap times the length of the air gap. So that's the magnetomotive force that we brought here on this coil. The flux is equal N times I, number of turns times the current we brought here, divided by the sum of these reluctances. Here is an equivalent circuit to this magnetic material. Okay, now we know that the magnetic flux density in the core of this magnetic material is equal to the flux of the core divided by the area of this core. and the magnetic flux density in the air gap is equal to the flux in the air gap divided by the area of the air gap. But as you can see here in this formula, the flux in the core and flux in the air gap is the same. So if you have the same area of the air gap and same area of the core, then you will have the same magnetic flux densities in the air gap and in the core of the magnetic circuit, and is equal the flux divided by the area of the core or gap. So in next video you're gonna see an example. And one more thing, if you always have an air gap here, you will always, if you have an air gap, you will always have something that's called a fringing flux. That's the flux that goes out in the air, in the environment, and it's kind of not so happy, not so fun. It's not good for an electrical engineering to have a lot of this fringing flux, but if the air gap is very small and the area is very big due to the length, so if the area is much larger than the air length of the air gap, then this is neglected, it's negligible. So usually we say, oh, okay, it's negligible, especially for the transformer, but yeah, in the air gaps we have some magnetic fluxes that go in the environment. So this isn't the most accurate formula. The flux core and the flux gap in reality isn't the same, but the difference is negligible. So yeah, and I'm happy that in my next video I'm going to do the first example. I hope you learned something, and see you in my next video.